4.4 optimization part 2. I'm going to do another example out of the textbook, and that we have a barn, and it says here that a rectangular pen is built with one side against a barn. 200 meters of fencing are used for the other three sides of the pen. What dimensions maximize the area of the pen? So we're going to do a maximizing optimization. So this part A is just that outside area. What is the biggest rectangle with 200 feet of fencing? So we have 200 feet of fence, 200 meters of fencing. And we want to maximize the area. So we need to go ahead and try to figure out some variables. And we know an area formula, it's length times width. But we got to figure out how we want to set it up. In this case, I'm going to go ahead and take my smallest sides, and I'm going to call this side X. And this should be equal. It's a rectangle. It's going against the barn, so I don't have two sides left. I just have this bottom side left. And because I have 200 feet of fencing, it's going to be 200 minus that 2x for a perimeter. So I'm going to use this data then to figure out a maximum area. So my max area is going to be the side times the length times width. So from here, I'm going to go ahead and distribute my x. This is my equation. I'm going to go ahead and take the derivative, set it equal to 0, and solve. So from here, when I solve my equation, I should have x equals 50. And then if I went ahead and I want to know the dimensions of this area, I have that it's going to be 50 for the side lengths, and I'm going to plug that 50 value in to get this width lengths. So it's going to be 200 minus 100, which is 100. So this is the max area for this pen. That's part A. Part B now says that a rancher plans to make 4 identical and adjacent rectangular pens against a barn, each with an area of 100 meters square. What are the dimensions of each pen that minimize the amount of fencing that must be used? Totally different problem. So I'm going to go back to my red and said, okay, this is what the rancher wants to do. And he wants this to be 100 meters squared per area. All right, so I'm going to go ahead and try to get rid of this right there. And I see then I still have an X I'm going to use for the side lengths, but what do I do? How do I figure out keeping that area but minimize the fencing? What dimensions do I need to put here? Well, if I take the whole area, 100 plus 100 plus 100 plus 100, that's 400. And it really is going to be the 400 and divided by the x. Because when I go ahead and put it in an area formula, and I'll put that a little side note over here, if I did the area for now this pen, it was 400 meters squared. If I divide it by x and multiply it by the side lengths to get my length times width, I get 400, which is what we have. We have in there that rectangular complete penned area is a 400 meters squared. So I need to go ahead and set it up as 400 divided by x. So I'm going to use this concept then and try to minimize my fencing. So if I go ahead and say I have this as my dimensions, x times the 400 divided by x, 400 meters squared, I need to say that my fencing or the perimeters of the rectangles that I need are going to be the 400x plus I have to count up the number of sides. 1, 2, 3, 4, 5. I have 5 of the x values, so I'm going to have 5x. So that gives me my perimeter, just counting up each of the sides that I'm going to use for fencing. So going ahead and using this equation, I'm going to find its derivative. P to the p prime of x, and I go ahead and I have negative 400 over x squared plus 5. I'm going to set it equal to 0. And then from here, when I go ahead and solve this, I get x equals 4 square root of 5. So from there, remember, they wanted to know what size would these pens be? What are the dimensions of each pen that minimize the amount of fencing? So this would be the minimized amount of fencing for the x. So this would be 4 square root of 5. And then if that's the case, I still have to find this dimension, which we're going to plug that x value into. So I have that. And then I'm going to go ahead and say I have the 400 over x. For the other dimension, we'll call this width, and we'll call this length. That might be easier. And then I'm going to go ahead and simplify this, and I am going to rationalize it. Uh-oh. I messed up somewhere. Hold on. What did I do wrong? Before I do that, that would be the whole pen rectangular area, not each individual pen. So let's go back and do this again. This individualized pen area is really going to be, well, let's go ahead. Let's do this. 400 divided by 4 square root of 5. Okay? But each of these, let me keep going with this. Rationalizing it. Okay, 20 square root of 5. This is for the entire length of this rectangular area, but this length area is going to be divided by 4 pens. So from here, I now have 5 square root of 5. So each pen dimension would be a 4 square root of 5 by a 5 square root of 5 dimension.